all about that. And just one more thing. So Gregor has been with IQC and is still nominally with IQC, although he's been whisked away to Innsbruck the last year. But anyway, so thanks for coming to join us.
Thanks, Joseph and Ray, for inviting me. It's great to be back. Gives me the opportunity to talk to my students here. This is it's kind of a it's one of my foundations work is always good, and we're always doing a little bit of foundations on the side, aren't we? The modern version is a three-slit experiment, and yes, I was so that was my PhD thesis, essentially working on an experiment to close one of the loopholes, one of the main loopholes in Bell experiments in general. Now, the structure is kind of as follows. Today, it's going to be all just background and theory, and if you already know, maybe you can learn some more or give me some comments. And on Friday, it's going to be all about experiments. So today, I'm going to write on the tablet PC so that you can have a PDF of my notes in the end. And Thursday, right? And Thursday. Did I say Friday? It's Thursday, regular time. And on Thursday, I'll need a lot more pictures, and so it's going to be in PowerPoint. Now, I have a little extra here today, which I thought would be maybe a good idea to do, and that's the relation between these theorems. That actually goes to maybe start with the literature that I used. I guess if you're really interested in Bell's inequality, you should probably buy this book, which is the collected papers of John Bell on foundations topics, speakable and unspeakable in quantum mechanics. He was at times, I think, quite appalled with the Copenhagenian imperative of not being allowed to speak about certain things. And he said, what is this nonsense? If I can say it, why can't I say it? Or if I can ask the question, why am I not allowed to ask the question? So there's a lot of this in his writings, also the idea of beables instead of observables. And so there's especially one of the articles in there, which is called Bertelmann's Socks and the Nature of Reality. It's very, very advisable, very good one. And some of what I'm going to talk about today is based on that. It's also based on, so the notation that I'm going to use, or some of the formalism, is also closely connected to the Stanford Online Encyclopedia of Philosophy article by Avner Shimoni that I think Joseph recommended for reading, so that you'd have for those of you who haven't read it, you'll maybe be interested to read it, and for those of you who've read it, it'll be a bit of a review. Good. So I'll start by just, I think Joseph already handled this, and interrupt me at any time if you think something's not clear, because we're trying to, a lot of this is very, it's not really physics, it's metaphysics, and you have to think. And I'll well, what I meant is in physics you can actually write it down in formulae, right? You can put it into math, whereas in philosophy it's often just text, and it's hard. So what I was going to say is that you'll find if you I think if you did an honest survey among the general public, and maybe among most physicists too, that most people are actually local realists, or realists in any way, right? We learn, in the course of this, we learn that some interpretations of quantum physics are not tenable, and this is shown by Bell's theorem. And that's a very, very strong statement. In fact, Avner Shimoni, I think, writes, or is it Mermin, says that Bell's theorem is maybe the most important theorem ever, in physics in the whole 20th century. That's a big statement, because people invented quantum mechanics and relativity in the 20th century, so why would one little theorem be so important? But it turns out that this really changes. I guess people like Schrödinger a long way back realized that, Schrödinger and Pauli realized that quantum mechanics was so different from classical physics that we should really be discomforted somehow. But it wasn't until Bell in 1965, or 64, 65, showed that you could actually measure this difference, that it was so manifest that people started worrying, really. Okay, now we'll go quickly through this EPR-Bohm argument, where there were two spin 1/2 particles. And we start them out in a singlet state. Okay, so we have something like psi equal to 1 over square root 2. And then it's up, down, minus, down, up. And of course, this is along z, and this is particle 1, and this is particle 2. And we just now imagine that we separate these particles in space. We haven't written down any spatial wave function, and I guess it would have to be a symmetric wave function for it to be antisymmetric in total. But we separate those, and then somewhere, far away from the source, we subject them to a Stern-Gerlach experiment. How do I draw this? Where then we measure the spins, and we know that the spins always give us discrete values. So we measure this parallel. If this is the z-axis, then maybe z should be a long propagation. It doesn't really matter. Okay, so there's two. It's not really going to be nice, so I'm not going to draw the left one. Stern-Gerlach. Now, we'll find that, of course, if each time we measure particle 1, we measure particle 1 as up, we'll find that particle 2 is down. And if we measure 1 down, we'll find that 2 is up. Okay, and that doesn't only hold in the mean, it just holds for individual events. And that's something very important, I think, that I think some people who think of this just as a statistical theory is that there are cases where quantum mechanics makes very definite prediction for individual events, single events. And that's the important thing. That's exactly what led Einstein and Einstein, Podolsky, and Rosen to conclude that something must be fishy there. So it's quite unpredictable whether it's up or down, right? So whether it's up or down individually is unpredictable. And you could say, actually, this is the only source of true randomness in nature. When something's entangled, and I haven't mentioned entanglement yet, but when something's entangled with something else, then its individual properties are completely random, and we can't find a reason for an individual event to happen. Now, we also know that a classical spin, if we had a classical little spinning magnet, and we put it through a Stern-Gerlach apparatus, so a classical spin, we would get some kind of distribution on our screen, which is basically just an elongated version, because you have this little dipole, and depending on how it's oriented in the field gradient, that's for the physicists among you. There's probably some mathematicians who don't know anything about field gradients, but that's okay. So that the field gradient pulls the dipole up depending on how it's oriented with a cosine law, and so you would just expect that if those classical magnets are randomly oriented little compass needles, they would just end up on some stripe on the screen or on your detector, okay? So then we know, of course, that quantum spins are different. We find that, at least for spin 1/2, we get two dots if this is the z in the field. So we get two accumulations of points, and if it's a higher spin, we get more. Okay. And surprising, this wouldn't even be surprising. I guess one could modify classical theory, and we'll try to do that in a bit, to show us these discrete values. But then it's a little more surprising that this, of course, happens in any direction, because clearly z can't be special in any way. So if you do the same thing along x, you'd also find two dots, and if you do it along y, you find 2 dots, and if you do it at any intermediate direction, you find 2 dots. Okay, and this is kind of surprising, but we'll see how far classical physics can go today. We'll try to find that out. So along any direction. Any direction. Now, we should go back to the singlet state here, and you all know that if I take the singlet state and instead of writing it in the z basis, I write it in the x basis. Of course, it looks exactly identical. X minus down x of x. This 1 and 2, 1 and 2. Which means that if I now repeat my observation with the Stern-Gerlach apparatus, this apparata, both oriented along x, I'll find the same perfect correlation. If I measure particle 1 up, I'll find particle 2 down and vice versa. Okay? Well, that maybe is not so surprising either. But then, but now Einstein, Podolsky, and Rosen would say, well, wait a second. In quantum mechanics, we're not really allowed to know x spin and z spin at the same time. Or, well, we can ask the question, we can measure, but if we measure z, then our x result should be random and vice versa. So there would be no more information. But here, so I'll just write this. I'll just say EPR. By observing particle 1, we can choose to predict some property of particle 2 with certainty. So with probability 1, we can, so we want, today we want to predict spin x of particle 2, so we'll measure ours in spin x, or in x, and then we'll be able to predict what x is on the other side. However, something hits us, and really we want to know z, so this time we choose z, and so now we can predict z for the other particle. In each case, the outcome will of course be random. We cannot force a certain outcome. We cannot force spin up in x, but we can know what 2 will be when we measure in x. So, and if I don't know how many of you have read the EPR paper itself. Anybody? Joseph, good. Ray, you too. Something that one can read multiple times. It's kind of has some very intricate arguments. And so this is one statement. We find that this exists, that quantum mechanics seems to allow this this prediction. And now we'll say because there can't be any spooky action at the distance, I don't know if Einstein ever said that himself about the spooky action at distance, but it's become, yeah, it sounds like Einstein, but I haven't seen it in print from him. Okay, if you find out, let me know. And we call this principle locality. Okay, because we just want to believe that in nature, as we know it, nothing happens instantaneously or without time delay, because that has a problem with Lorentz covariance. As soon as you have something that happens instantaneously, it can also happen backwards in time, and you keep worrying. You worry about causality. Although causality is not, it's a different concept really. Okay, so we have locality. So because there is no such spooky action at the distance, we don't disturb the particle 2 We don't disturb particle 2. And therefore, if we can, according to the EPR paper, if we can predict with certainty a certain physical quantity without disturbing the system, then we call this an element of reality. Okay, so this is something. If you have something in your system that you can predict with probability 1 without doing any measurement or disturbance on the system, then this should be a real property of the system, right? It's not just real as in non-random, I guess. So therefore, we can choose what is real for the second particle. And this principle is reality. The EPR argument. So now the argument goes that if these properties are real, then they must exist in the system. Okay, but they exist in the system. However, quantum mechanics doesn't tell us which outcome we will see. Okay, and therefore they conclude quantum mechanics must be incomplete. There's something that is obviously that we can predict, but quantum mechanics doesn't have a reason for it. It must be incomplete, and so they conclude that there must be something below, some level below, that will tell us for each of these choices what the outcome will be. Okay, the trick is really that we can choose to predict which the sigma x or the sigma y, the spin in x or spin in z, that we measure, and since we can do that choice without disturbing the other system, both of these properties should be somewhere hidden in the system. Okay, that's the conclusion. It's formulated differently. It's formulated as to, since there are no hidden variable or nothing extra in quantum mechanics must be incomplete, and it should be supplemented with something else. So therefore, these properties must exist. Quantum mechanics is incomplete. And that's completeness. I mean, they define precisely what they mean by completeness. Okay, and they actually conclude from this that a more complete description should be possible. And this is generally cited as the idea of hidden variables. Some variable that will tell us what spin in x direction is and what spin in z direction is. Just that quantum mechanics is not powerful enough to treat that in the theory. All right, so let's do an example. How do we construct hidden variables? Because they go way back. They go back before Bell, and there've been quite a few proofs of the impossibility of hidden variables. And I think you went through this, right, Joseph? The no-go theorems for hidden variables. You didn't get to those. Okay. All right. Well, we'll see. I'll mention one thing, I think, in a bit, because Bell was essentially. So now I'm gonna have an example of a hidden variable theory, very simple one. Okay, and even long before Bell, people tried to find proofs that hidden variables weren't admissible. However, over time, all these proofs got deconstructed and errors were found. And I think that actually one of these proofs triggered Bell's interest in this whole thing, because he found a flaw with it. That was von Neumann's proof, and I think this triggered Bell's inequality in the end and Bell's theory. So now let's do this example. So an example of a hidden variable theory. I said before that we have this little magnet in the gradient, and let's write down the force on the magnet in the field gradient. It's pretty simple. It's just some constant f here, which relates to the magnitude of that dipole, and then the angle that dipole has. So if there's a gradient, I guess I can draw field lines for the physicists among you, and then just imagine a little magnet, red and green, right? And depending on the angle, one of them's, there's one end is pulled into the weak field, and one is pulled into the strong field, and so there'll be a force, a net force in that gradient. That's going to be f cosine theta along the direction of the gradient, of course. And now we'll just quantize that under quotes. And we'll say that we just postulate a new force law, which is f cosine theta divided by absolute cosine theta. So it'll simply be plus or minus f. Okay? And this way we simulate quantum spins. We just say, okay, the force, for some reason, the force must be quantized, and it'll be quantized by this value, whatever it is, maybe just a phenomenological parameter. So now let's go back to this case of the singlet, okay, and analyze this. We'll just assume that the singlet consists of little magnets, pairs of magnets that are emitted from the source with opposite orientation. Okay, we'll just assume that they're emitted with a random angle, any direction in I guess on the sphere, but always with opposite angle, like this. And every pair of magnets has a different individual direction. That's our hidden variable, okay? And one of them is going to point up, and one of them is going to point down along that direction. So our singlet, under quotes, will be a pair of these magnets with some random orientation, but oppositely poled. And now clearly, if we do a measurement on the system, maybe I should do a little drawing again. So here are two magnets. One of them is flying off this way, one of them is flying that way. And then again, we put our Stern-Gerlach analyzers to see which direction it is. Now, of course, if we measure in z and z direction, if we measure in any direction, we'll find that magnets that have their orientation parallel to that direction will produce perfect anticorrelation. Actually, in any direction, pretty much you will produce perfect anticorrelation, right? Because essentially what I've done here with this cosine over absolute cosine force law, if, that just postulates that even if the spin, the magnet is like this, if it just has a slight tilt towards one side, it's going to go with the same force in that direction. Okay, so it's just going to separate randomly. If the random orientation is slightly to this side, it's going to go like this, and if it's slightly to the other side, it's going to go down. So for every pair, since the pairs share their precise direction, they will do exactly the opposite movement for any given Stern-Gerlach direction. Okay. That's a very simple hidden variable model. So this model I'll just write this down. So because the two magnets share the precise axis, I guess, they will produce perfectly anti-correlated results if we measure, so for, I guess, for parallel spin measurements. And if you, this is kind of important. If you, I don't know which one of Bell's articles it is, but he starts out by saying the philosopher from the street is not very impressed by EPR correlations because they're not so surprising. They're only surprising if you look into, or if you believe in the that you can't simultaneously measure non-commuting observables. But otherwise, if they were classical observables, they could all be anti-correlated or correlated, and we wouldn't be surprised about it. Like if you I don't know, had a coin in your pocket and for some magic reason that coin was split right down in half, then if I gave you one half, if I gave Ray one half and he would have heads, I would have tails. Okay, so there's perfect anti-correlation in this basis. Now just imagine that this coin also is blue on one side and red on one side, and the blue and red property is also perfectly anti-correlated. So there's nothing magic about this part at all. And this is why we can actually formulate a hidden variable model about it. Okay, we can choose to introduce hidden variables that will produce these perfect correlations in any basis. Okay, so now you wonder, well, what's this whole EPR argument about, right? If this is so trivial, and I think it's because, it's because, of course, you also want to respect the other properties of quantum mechanics. But then it's also the reason why many people weren't so bothered by it until Bell showed that there's actually a measurable difference, and we'll see that now. Because now we'll do something else. Instead of always measuring in parallel direction on both sides, we'll now try to measure in slightly misaligned directions, or misaligned directions. So we'll measure, say, in Z on one side, and we'll measure in X on the other side, or 45 degree. What should happen if I measure Z and X for the singlet? Anyone? What do I get? Not you guys. Chris. Random. That's right. Yeah, you should know because you have a qualifying exam on Thursday. Okay, so if I measure in X and Z, we'll see. It's not on my list, but so if we measure in X and Z, there is no correlation. Okay, if you just and the way to prove this, be a nice assignment, is to, it's almost too simple. Is you rewrite that singlet state for one particle in the Z basis and the other particle in the X basis, and you'll find that there is no correlation. Okay, well, a very trivial assignment. I'll write that down. So now let's measure in different directions. Say Z and X, and we find that for Z and X, there's no correlation. But then, if we actually go back to our model here, we'll find that it does that too. So for Z and X, if we do this, there's a problem with infinite precision here, but if we were to believe that this actually works, we'll find that this model at Z and X produces no correlation either. Wow, it's even better. So it produces that property too. So what do we have to do? We have to go in between. Okay, that's the whole thing behind Bell's theorem, is that you do measurements at in-between angles. And so we'll calculate. I should say up here that so this thing, I should emphasize this random orientation, this is our hidden variable. In case that wasn't clear. So now let's do other angles, and I won't do the calculation. So for arbitrary angles A and B of the Stern-Gerlach apparatuses, angles A and B, we just find that the probability to measure up and up along A, I guess. I don't know. I should actually write this different to be consistent with what comes later. I should write this like so. P up of A and B actually, will be equal to P down, AB, and that'll be equal to 1 over 2 pi A minus B, whereas the P up, down, A and B is equal to the P down, up, A and B is equal to 1/2 minus 1 over 2 pi A minus B, absolute. And you can, that calculation is really simple. You just have to average the cosine. No big deal. Now, quantum mechanically, of course, it's different. That's also a nice exercise. Quantum mechanics, we find that P up, AB, E, I'll just leave out the middle here, is equal to 1/2 sine square of A minus B. And then the P up, down is equal to 1/2 minus 1/2 sine square, which is of course the cosine square, A minus B. So we see that our hidden variable model kind of fails. It fails to reproduce that precise quantum mechanical dependence. But then that wasn't really a very smart hidden variable model. Could we do better? The question. Let's just plot. I have a plot here of these functions. So here's the two functions. The quantum mechanical one, nice sine curve, and then this simple essentially straight lines of our model. Okay, the difference is actually not huge, and you see that it reproduces the quantum mechanical one at these points where, at 0, difference, this is in units of pi, and so at identical directions, at opposite directions, and at orthogonal direction, our model precisely produces the quantum mechanical expectation, or the quantum mechanical probability. However, in between, most notably there at pi over 4, we have quite a bit of a deviation. And it turns out that this is all that's behind Bell's theorem. Okay? Turns out that you can find an inequality, and that inequality shows that no hidden variable model that you can produce will be able to reproduce this curve exactly. Now there's some caveat here. When I say reproduce this curve exactly, I also mean with 0.5 amplitude. Okay, so a scaled down version I can produce too. So with a different model, I could have a sine curve that basically does this. That doesn't go down to 0 and up to 1/2. And it's 1/2, of course, because we cannot predict we don't know whether it's up, or down, but we know it's either one of the two if we're at these points, right? So each of them has to have probability 1/2. So all 4 probabilities, of course, will sum to 1. The up, down, and the.
How much can you lower down? 0.5, so that.
Well, 1 over square root of 2. Of course, in the later one. Good. So we saw that our naive model, I call it the naive model, reproduces these points here. at 0, pi over 2, and pi. And the question is, could we do a better model? That's the question. And the answer is no. And we call that Bell's theorem. So Bell's theorem is a theorem that says you cannot produce hidden variable models of a very general kind, and we'll look exactly into what the conditions are, that reproduce the quantum mechanical predictions for these correlated or entangled systems. And to do that, he developed an inequality. So there's Bell's inequality, and then Bell's theorem says that quantum mechanics is different from that inequality. So here's the general setting. And that's also a drawing from Bell's book. The general idea is that you have some kind of elongated apparatus, and you don't really need to talk about spin or any specific property. It doesn't matter. All that matters is that you have at least two possible outcomes on each side. And typically, in contrast to quantum computation, these are labeled plus and minus 1 rather than 0 and 1. But you can label them anything you want. So this is side A and this is side B. There is some, so in this drawing, when he talks about that, he says this apparatus should really have some kind of, you start it and it should tell you whether it's ready. It's sometimes called event-ready operation or event-ready detection. And I think that's kind of a side thing. And then you also think about this apparatus as being spatially extended so that locality can play a role. So you do these two measurements somehow far apart, and you do have some external devices that inject a signal, essentially the angle A or B, into that apparatus. And it'll be very important that these A and B can be chosen independently from anything else that happens. So with this setting, we can derive an inequality. So we'll just assume that there exists some kind of probability distribution, A, B. So that's the outcomes conditioned on the settings A and B, and some lambda. And this lambda we call the hidden variables. It could be anything, okay? It doesn't have to be a real parameter. It could be discrete, it could be a vector, it could be a field, you name it, you got it. Doesn't matter. Then A and B, we'll say, are either plus or minus 1, so that the apparatus will output two different answers. That's one of the conditions. And then 2. Now comes the tricky, or I guess Bell's invention really. We'll assume the following. We'll assume that P, A, B of A, B, and lambda is equal to P, A of A and lambda times P, B of B and lambda. And we'll call this locality. And you shouldn't take this lightly, because that's a very strong statement. Or, well, depends. Maybe a matter of taste. Because any I guess probability theorist, statistician will tell you that if your probability distribution factorizes, that already says a lot about correlations that you can expect. Okay, and it factorizes in some variables. It doesn't factorize, so we don't assume that it factorizes in lambda, right? That's the whole point, that somehow there's hidden variables in the system that are common to the two sides. But we do assume that the outcome on the A side does not depend on the B parameter. That's the parameter independence. And we also assume that doesn't depend on the B outcome. And so usually, and it was shown by various people, that this condition is logically equivalent to saying that P, A, B, of A, B, and lambda is, what did I write down there? No, I'll just say it. That, so this is logically equivalent to what we call parameter independence, meaning that the left side is the outcome on the left side is independent of the setting on the right side, the setting, so that's the parameter, plus outcome independence. So we also want to demand that the outcome on the, which one, this is your left side, is independent of the outcome on the right side. Okay, and we can, if we write this separately as statements, one can show the logical equivalence to this formulation. Yes, please.
Just to clarify, those are three different lambdas, right?
No, they're all the same
They're
lambda.
all the exact same lambda?
They're all the exact same lambda.
Okay.
So lambda is supposed to
It's an
exist.
variable for the entire system.
Exactly. It could be, you know, it could be attached to the particles. It could just be a field that's throughout the universe. You don't really
it
care.
could be multiple.
And
It's not one scalar, right? It stands for any amount of information.
Is it
Right.
pathological?
well, we will just later on we'll just assume that it's a measurable, that's somehow defined on a measurable set. But that's a very general assumption. It's just so that we can extract this P at all. Otherwise, we only have some kind of frequency. But then, yeah, but this frequently comes up again. You know, what is the hidden variable? And maybe people haven't thought of the most general possible hidden variables, or people haven't thought of the hidden variables varying in time. I mean, I was involved in kind of fighting that down, if I'd say that. Some two mathematicians coming up with this thing, no, in Bell's theorem, they really overlook time. If we make this time dependent, then suddenly we can't do averages anymore, and there's no Bell's theorem. And of course, I mean, if you once you've really understood this, you realize that it is pointless. Whatever you add on, because whatever deterministic stuff you add on can be packed into lambda. Because I can make lambda a database of all knowledge in the universe, with all classical physics to predict whatever happens in the future. It shouldn't matter. Okay. What's really important is that we assume that we can do local experiments. That is an assumption. Okay? I mean, we can justify that assumption saying that, well, if these are really far separated, we would like to believe that we can choose freely an A here, and it wouldn't be known at B over there. But some people would contest that. Okay? They would say, well, really, your instrument is remote controlled by the hidden variable. The hidden lambda chooses your A. Okay? Which doesn't matter if I say, well, A is what I inject. I don't care what the device does. I'll just use that to build the correlation in the end. And then they will have to say, well, you're remote control. So in a way, this freedom of choice of the parameters is a very philosophical, fundamental thing. It just postulates that we have free will in the end somehow. Okay, because if I deny that, if I say that I control the experimenter and I control his choice, then I cannot derive Bell's theorem.
You actually need to assume free will to make the argument go.
I think
I
so.
know it's something, Luca, you've been, do you have some criticism of that? I mean, it's known, the assumption of free will. You know, I thought you had in your thesis, I think Cosmin pointed out to me. I don't know if you want to grind that axe
like
right now.
speaking about such stuff. You cannot even define free will.
Of course not. No. But in some version of this, we basically assume that we can. There's an assumption. We can do an assumption that parameters A and B are statistically independent of the other things, right? That's just a mathematical assumption that we use.
Yeah.
The problem is that there are two problems. First, that independence can be statistical, but not so physical and logical independence.
Right.
That's the first point. They can be physically independent, but that since we are speaking about probability,
Yeah.
we are really making an inference about information. So I can, from for example, little a, I can infer something about the past, and that can tell me more about the little b.
Right.
Then there is another problem that when you have two theories
Yeah.
working at two different scale levels, take statistical mechanics and I don't know, continuum mechanics. What do you call boundary conditions in one theory? Which means the conditions which the mathematical input, which is not given by the theory but is given by you, can correspond in the other theory to something which is not decided by you. That's a big problem that nobody has up to now.
Yeah, for sure. All right. Yeah, there's lots of subtleties here. Okay, so and one should, I think the only message I have is you shouldn't be discouraged by old professors discussing the same things that you worry about. So number 3 was basically what I said, freedom. We call this freedom sometimes. That A and B can somehow be chosen independently of lambda.
So mathematically, really, do something that A and B are independent of lambda, that they're independent variables, and then
Right.
the way we would think about that is that, I mean, because you have this superdeterminism argument, right? That
Of course.
right,
Yeah.
that A and B, little a and B, were
Yeah.
determined by the Big Bang, and so it's in the backwards light cone, and
Exactly.
really this notion of independence is. I mean, then of course you're looking at to explain violation of Bell's inequality. It's massive conspiracy.
Of
that,
course.
all experiments you were to perform were determined in the Big Bang, and
Of course.
Just
Or
the
even
right
are
way
we
to-
even able to choose randomly at all, right? Are there random numbers? I think you almost need to assume that too.
well, one thing I was wondering if you could do to overcome this, and I think I concluded it didn't help, but I was wondering if you could have the randomness. The randomness is the outcome of a quantum process that might buy you something.
But if you assume quantum mechanics, then there's no point in doing any tests of Bell's theorem.
Yeah.
Maybe that's the problem.
So that actually, I had a question with that. You said lambda can be anything, but it can't be the quantum state psi, because then right away, equation 2 is wrong, right? Because you already said that.
Oh no, you
If
can
I-
do equation 1, but I didn't see. The thing is, I didn't actually say what P.
Then I have to-
What I didn't say is that of course, what we assume here is that we have that these functions A and B, right, will have definite values. So A and B should have definite values that depend on lambdas. A and B.
Well, I think it can be psi. It just can't be the psi that's associated with the Bayesian update after you do a measurement little b and get outcome big B. You're gonna have to update your state on the other side, right? So lambda could be the singlet, but it can't be the state that gets updated as a result of the measurement selection on the other side.
Yeah, so it doesn't know the outcome.
Yeah, so it
in that
can't be anything that depends on what you choose to measure, what the outcome of that measurement is, but it can be the information associated with the singlet, which is your preference.
Oh yeah, for sure. Because quantum mechanics doesn't tell us what A and B are, right? It doesn't. It doesn't predict A or B. We have psi, and we can predict the probabilities for A and B, but it doesn't give us an outcome.
But that's what you're asking about, is the probabilities, right?
Well, that's what I'm. Well, actually, these p's. That's not very good. These p's are actually not really probabilities. These p's are. Well, they are probabilities. But what's behind that is that I want. I guess what I really want is that I have a function. That I have two functions. I should put this somewhere here. That I have two functions A and lambda, and B b and lambda in the end when they're localized.
Right.
That will give me values a and b. My notation is a little sloppy now, of course, because I use a as a variable in p and also as a function of lambda. Please.
I guess what's confusing me then with the last clear discussion, so if our hidden variables then should deterministically determine whether or not what the outcome values for A and B are going to be.
Right.
So the quantum state doesn't do that though
Exactly.
So we're saying that lambda cannot be the quantum state then?
It can be the quantum state.
It can or cannot?
It can.
But how
Or
can
you can add the quantum state. Like you could say lambda is the object formed, or the pair formed of lambda prime and the quantum state.
But if it's quantum state alone, how does it determine the?
It doesn't.
So it has to be more than the quantum
It
state.
has to be more.
Okay, that's what I was.
Yeah.
That's what I was
No,
getting at.
I think it would have to be more for your hidden variable theory to be a hidden variable theory.
Okay,
To reproduce the statistics.
it has to be more than the quantum
Oh,
state.
sorry, that doesn't make sense. Hold on.
Well, I guess whether you attach quantum state to lambda in addition or not probably doesn't matter.
But all this discussion is about one quantum state, which gives
Yes,
me
but one copy.
So I just want to reproduce that particular behavior for
Exactly.
that quantum state.
Yeah. Yeah.
Would it be done, do they really have to be independent, or could they be multi-valued in lambda? So,
You mean could lambda be multivalued, or could A and B be multivalued? So here's one, and I don't know if whoever of you has read Joy Christian's paper. I don't know if you have. It'll drive you nuts, but it's okay. There's exactly the problem. He's assuming that the outcome functions, A and B, are actually
Quaternions?
no, they're not quaternions. They live in an 8-dimensional space. What's the space called? Yeah, it's quaternions, but what's the geometry? Oh man, doesn't matter. Okay, and so, but of course, what we are trying to mimic with this model is what I do in the experiment, where I get a binary answer, and he just doesn't accept that. Right? He takes correlations of multi-valued real objects, and with those I can do much more. I think that's one of the very, very important constraints is that I have to give a binary answer. Okay, my hidden variable theory has to give a binary answer to determine. I mean, that's what I measure. I measure clicks. I measure frequencies in the end. And if you have a theory that gives real valued outcomes, you can produce different things.
And so what does he do? He just refuses to accept the experimental outcomes, or what?
So his theory uses what's the geometry of the one forms, two forms, and the three form
Oh,
on the sphere. What's that geometry called? What's that?
well, whatever the term, but
It doesn't matter. Okay.
I mean, is he concerned with explaining experimental outcomes ultimately?
Well, you can never get that out of him. We tried for hours. That I said, well, your theory has to give me a value. I said, oh no, but the average will be this times this. And I said, but that's not that's not a hidden variable theory. And if you can't explain the individual outcome, then it's not a hidden variable theory. It's just a theory that sort of mimics taking the quantum expectation value over a large ensemble. Okay, but that's not what I'm doing in the experiment. Otherwise, it's basically a rewriting of some small part of quantum mechanics in some other mathematics, but it doesn't give me the individual outcomes, and that's where it breaks, and he doesn't seem to realize that. Okay, so now having these, we take the correlation. So basically, we average these functions a times b over the space in which the hidden variables lambda are defined. Okay, so lambda are supposedly chosen randomly by some entity, the system, from some space, some measurable space, Also, this is usually written as E of A and B for some reason, and we'll just define this as P, and now I use plus plus because the up and downs are so hard to read. I use plus plus 2 because it's plus and minus 1. You can think of this as spin up and down. AB minus P AB. Here's this plus minus. And this is minus plus AB. And of course, this correlation itself will be in the closed interval minus 1 and plus 1. If these are probabilities. This is the definition now. We'll just say that, and then each of these individual ones, P plus plus A and B, is equal to P, and this is just related to the previous definition, plus 1 of under the condition of A, B, and lambda, and we said that this should factorize, so it should be P plus of A and lambda times P plus of B and lambda. So this is now, maybe I'll superscript this with a lambda here. I should do that. And so then I can calculate E lambda in B, because this definition up here will also be the one that we'll use in experiment to determine what E is. Okay. So then E lambda in B is equal to P plus. Oh, I don't need it here really. A lambda minus P minus A lambda times P plus B lambda minus P minus B lambda, right? From this definition here and that factorization, we can get this part. And okay, it's just the same. And now we'll also note that, of course, this is also in the same interval, minus 1, 1, and that one, 2. And now we'll use, that's the way how Shimoni derives it. And I like it because it gives us this mostly used version of Bell's inequality, which is the CH-SH inequality, which is kind of a little more symmetric than some other versions. And in order to prove that, we use this lemma. So if you can't read my handwriting, you can read it always in Shimoni's article. For 4 numbers, Q, Q prime, R, and R prime, in this interval minus 1, 1, the expression S, which is defined as Q times R plus Q times R prime plus Q prime times R minus Q prime R prime, will be in the interval minus 2 and 2. Okay, that's the theorem, the lemma. To note here, all of these Bell inequalities typically have expressions like that where one thing has a minus out of 4. Okay, that's just if you see that in somewhere, you'll recognize it. Now, and the proof goes as follows. I never do proofs. This is the first time I do proof. Because S is linear in all arguments, or in all what we call variables, I guess. S will take its extremal values at the corners of the polytope of, I guess, Q q prime r and r prime. Which means that we only need to consider q prime, r, and r prime to be plus or minus 1. Right? And now we can we also find that because that's the boundaries, and we also find that then algebraically the largest value of s would be plus or minus 4, right? Because each of these expressions could then only be I mean, potentially this could be 1, 1, 1, and minus 1, and so it'd be 4. That's another thing. So we also know that s has to be bounded then by minus 4 to 4. And now we'll also do a smart rewrite of s. We'll write it as q plus q prime times r plus r prime minus 2q prime r prime. Right? And now we'll look again at the. So I should put here this so the extremal values have to be bounded by this. And I'll also write it like this. So now we know that since we only have to consider these to be plus or minus 1, we know that this thing here is, or actually both of these expressions, should be in minus 2, 0, or 2. Right? If they have the same sign, they'll be 2, or plus or minus 2, and if they have opposite sign, they'll be 0. Meaning that the product of this, that's a good, the product of this whole expression will be either minus 4, 0, or plus 4. Whereas this part here on the back can only be plus or minus 2. And so this whole expression should be in minus 6, minus 2, plus 2, or 6. But since we've already determined that it can't be plus or minus 6, we know that this expression can only be plus or minus 2 at the most. It's quite neat. So we've proven this. Okay, so now we'll define an S lambda, which would be the E lambda AB plus E lambda A B prime plus E lambda A prime B minus E lambda A prime B prime. And because of our factorization condition of before, where we had, so we'll just say that Q is equal to P plus A lambda minus P minus A lambda. And then Q prime, I won't write down all of those. A prime lambda minus P minus A prime lambda. And so on. For R and R prime, we then find that our lemma applies and S lambda must be between minus 2 and plus 2. Good. And now we haven't even integrated. So this is just for a single outcome in a way, for a single instance of the hidden variable. And now we'll still have to do one more thing. We'll have to average over the space in which the hidden variable is drawn from. So we'll define an S of, and I called it rho here. Ray won't like this again, I know. It's all right. I'm in charge. So this would be S lambda, rho lambda, d lambda, and rho is basically the space, so that I guess integral rho lambda d lambda is 1. Okay, so that's just our probability space. And likewise, E of rho would be defined as E lambda, rho lambda, d lambda, or whatever space that is. I won't even write the boundaries down. And since we're averaging a quantity which is between plus or minus 2, we can only get something that is between plus or minus 2. Okay? So we conclude that S rho, magnitude of that is smaller or equal than 2. And this is Bell's inequality. And there's a lot of other, many different derivations of that. Some that are a bit more elementary, and that they just look at sets and so on. In the end, that doesn't really matter. But in fact, the important things is, I guess, that it's, and I guess some people say, you know, this inequality has been discovered long before by Vorobiev or whatever his name was, Russian probabilist, except that it had no connection to physics, so it didn't mean anything. But I guess it's a general statement about factorizable or correlations of factorizable functions. If you have that, you can derive Bell's inequality. It has nothing to do with physics at this point, and we only happen to use it for hidden variables because that factorization seems to be equivalent to locality. But in general, the inequality itself says nothing about the physics behind it. And that's the beauty of it, too, because it kind of applies to all possible scenarios of hidden variables. So the only assumptions were that we had some functions that gave us defined outcomes, defined binary outcomes. And then all we do is average. And it's kind of, I sometimes say that this is a second order correlation function. I don't know if you like that statement, but if I say that this E here, or this thing A and B, is a correlation function, then S is kind of a higher order correlation. I kind of look at, I will plot in a second. I will plot E, and S kind of probes how E changes as I use multiple values. So it's basically sensitive to that deviation that quantum mechanics has from any local hidden variable model. How am I doing in time? It's almost over, right? Okay, no, I can finish that, I think. So, you do? Oh, that's all right. You're allowed to go. Right. So now,
Thursday, you know, so.
okay. Let's remember our naive model. Our naive hidden variable model. We had that P++ of A and B was equal to 1 over 2 pi A minus B. Oh, sorry, A minus B. And if I now calculate EAB, I will find that it's 1 over pi A minus B minus 1 plus 1 over pi A minus B. That's the basically P plus 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 P minus 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 P plus minus minus P minus plus. Yes. And that is 2 over pi A minus B minus 1, which at least for the interval minus pi to pi stays in in the right range. You know, this model has a bit of a quirk when you go to large angles because it doesn't respect the cyclic property, but that's all right. And now comes, so this was Bell's inequality. And I guess I should write this here. The specific version that we have here is also called CHSH, after Clauser-Horn-Shimoni and Holt. But you'll hear more about this on Thursday. And now, so this was Bell's inequality, and now Bell's theorem is completed by noting that quantum mechanically, for our state psi is equal to 1 over square root of 2 up, down, minus, down, up. If I want to calculate P plus plus of A and B, I basically have to calculate the following probability. I have to calculate the projection to up along A and up along B with my state psi. And of course, everyone in this room can do that, but I'll still maybe sketch so up along A is simply cosine A over 2 up along Z plus sine A over 2 up along Z, and I've neglected the azimuthal angle. Okay, so this only happens in the XZ plane so far, but we don't need, it's interesting, by the way, an interesting side note that when we study violations of Bell's inequalities, we don't actually need the full Bloch sphere. We can live on a plane and still see that. Interesting point. Okay, this was up, and then down is just with a minus, of course. Minus, and if you plug this in, you can do this. Well, I'll plug it in for you. Plus AB equal to 1/2, and then we have cosine of A over 2, cosine of A over, no, wrong sign, minus sine A over 2, cosine A over 2, and of course that will be equal to 1/2 sine square of A minus B over 2. And then from there, I find that the quantum mechanical E of A and B is just minus cosine theta. And I should have a plot here of that. So that is that. Here we have a plot of E. Looks pretty much the same as the plot of P accidentally, except that the scale is different. Goes from +1 perfect correlation to perfect anti-correlation, right? We have perfect anti-correlation for the singlet when we measure identical angles. And if we flip one by 180 degrees, we measure perfect correlation. And again, at 90 degrees, we measure no correlation at all. And now notice these points here. I'll just mark them in there. And this is where we get the strongest deviation of our EQM from the E hidden variable that we had before, the E lambda. So we're going to exploit that in Bell's inequality by choosing certain angles. So we'll choose A 0 degrees, A prime equal to 90 degrees. I should do this in pi, huh? Pi over 2. B equal to pi over 4, and B prime equal to 3 pi over 4. Famous Bell angles. And we could have chosen some others. So this is just what gives us the maximum violation, and we find that SQM at these values is equal to minus 1 over square root of 2, minus 1 over square root of 2, minus 1 over square root of 2, minus, this is plus 1 over square root of 2, and this is 4, which is 2 square root of 2. So magically, we've constructed this parameter S such that it has the minus just in the right place. Actually, you can have the minus anywhere. It doesn't matter. Clearly, the Q prime, R, and R prime were just, you can shuffle them as you like. You can actually then, if you do this, you can put in more absolute bars into here, 2 more if you want, and you will still have a Bell inequality, a valid Bell inequality. It just, depending on where the minus is, you will have to relabel perhaps the angles or so. And anyway, we find that this is 2 square root of 2, which is certainly not smaller than 2. So this is certainly larger than 2. So we conclude that the correlations, I guess, this is the maximal violation of Bell's inequality. And all maximally entangled states give us this value, at least in 2 by 2 dimensions. In 3 by 3, things are a lot more interesting, because in that one we have a maximally entangled state that is different from the maximally non-local state, as they call it, which is interesting in itself. But it's just the structure of the inequality that makes that. We also find that separable states don't violate the inequality. What else? I guess the only thing that, well, I could do that on Thursday. I just want to say I did it all for spin 1/2, but then all of the experiments that have been done, or almost all experiments have been done with photons. And all we need to do is kind of map the terminology, but nothing else changes. I did it with spins because generally, I guess we learn when we study quantum mechanics, we learn more about spins than about photon polarization. But it's really no difference. Something else that I wanted to say. Yeah, I had more on the relation to the Kohn-Specker theorem and to the GHD theorem, but I think I'm gonna skip that unless. Please.
Hidden variable theory.
Here?
So yeah, I'm concerned with 2 and whether that's what we really actually mean by locality. So, I mean, suppose you took the simplest possible model that you could come up with for a hidden variable theory, where lambda was simply the propagation of some quantum field between, the 2 ends of the system.
Right.
Right, so you took it to be a photon or a scalar field or something like that. And, I mean, there's a simple calculation you can do in quantum field theory where you calculate the propagator of this field between 2 points that are space-like separated. And what you find is that what you'd like to say, and I think this would imply that that correlation should be 0 if they're space-like separated, but the quantum field theory prediction is not. I mean, the correlation falls off exponentially outside of the light cone, but it's not 0. So
I don't think it has to be 0 just because of that. It can still be correlation. The question is how much.
Well, but it wouldn't be a product. I mean, you'd have something, it'd be something more complicated that presumably the farther you went away, it would become more and more like a product, but it wouldn't quite be a product. So, I mean, is that what you really mean by locality in quantum field theory? That's my question.
There was a paper by Morgan in which he analyzed this, and I think he arrives to the conclusion that this quantum field theory violates also the premises. So,
okay.
Yeah. So
yeah.
There's
right. Of course. No. I mean, we don't necessarily. Clearly, quantum mechanics doesn't have to obey this, right? Obviously. Because this is a hidden variable theory.
But,
No, you-
but the hidden variable theory should be quantum mechanical too. That's my point.
Oh,
So I mean, it's
or
the hidden variable theory.
you think
simplest
we shouldn't demand of hidden variables more locality than we demand from
of quantum field theory.
quantum field theory?
Yeah.
Why?
Now, isn't this, so I always think of quantum mechanics as a subset of quantum field theory.
Yeah. Well, I would think so.
And
too.
then-
And if that's the case, I'm saying that might not be true. You have to work out the details. but-
Well, it is not true, right?
But
That's
EPR
what turns
state
out.
itself. EPR state itself, this is not true.
This is violated. That's the whole point, right? We violate the Dillon
No,
equality.
I know.
But
I understand.
you're wondering whether it's fair to demand this of the hidden variables, right?
Yeah, exactly.
And I think I guess we have to clear out the room.
So keep your questions
But,
for Thursday,
yeah.
let's get back to that.
Is that Peter Moore?